So hello, everybody. Today we have another invited speaker at the DataLearning working group talking about Martian Atmosphere Reconstruction through long short-term memory network. So we are very happy to have Davide Amato, which is a new lecturer of Imperial College London. And yeah, he will give us the opportunity to have this walk on Mars. So the floor is yours.
Thank you, Rossella. Assuming you can all hear all right.
Yes.
There you go. Okay. Yeah, thank you for the introduction. Today I'll give a talk essentially on in understanding the behavior of the Martian atmosphere for the purposes of entry-descent landing. By entry-descent landing in spacecraft engineering, we mean the final phase on an interplanetary mission, when you actually want to land on the planet and use the atmosphere for braking. So I'll start by giving an overview of what is how entry-descent landing works, especially in terms of guidance, how we steer the vehicle around, and why we found the problem that needed a deep learning algorithm to be solved. And I'll just highlight some results and have a thorough discussion. Before going on, I'd like to thank Jay McMahon, who's my co-author on the article for this work, and he's been my supervisor doing a postdoc at the University of Colorado Boulder. Okay. So entry-descent landing, as I was saying, is the final phase of a landed planetary exploration mission. Like, for instance, I don't know if any of you have seen the video. Let me see if I can play this. The video of the entry and descent and landing of the Mars 2020 rover. They arrived at Mars in February of this year. So this phase of the mission starts from what we call the entry interface, which is kind of like conventional altitude that limits the start of the atmosphere, which for Mars is at 120 kilometers. Once the spacecraft gets there, it encounters a lot of atmospheric drag, and it's a very stressing environment. And since there is a light time delay, we need to have a lot of events that happen on the spacecraft, all in a rapid succession, and this has to happen in full autonomy. There's simply no time to send commands from the ground. And you can see here, for instance, that for Mars 2020, we have deployment of a parachute, and then a sky crane, which uses rockets to deploy the rover. So all of this, of course, is very complex, and it's a very delicate phase of the mission. Now, this is the let's say that Mars 2020 is the present. For the future, if we want eventually to enable crewed missions to Mars, so in preparation or to carry astronauts to Mars, for instance, we will need 100 times increase in landing accuracy, which at the moment is around 8 kilometers, maybe a little less, maybe 5 or 6. We want to decrease that to a few meters, well, to 50 meters ideally. And also we need to increase the landed mass, of course. So right now, the heaviest payloads that we're able to leave at Mars are things in the order of Mars 2020, which is the size of a small car. Eventually, if we want to build a Martian base, we will need to increase this to at least tens of tons. Of course, the EDL, entry-descent landing process, is quite delicate, also because we have large uncertainty in the atmospheric properties of Mars. We have uncertainty also like in the atmospheric properties of the Earth, for instance. The difference with Mars is that with Mars we have much less data, so we don't know the atmosphere so well, and so we don't really know the magnitude of the braking force that's acting on the spacecraft. Also, we would like to land in different regions of Mars at mid and high elevations, which hasn't really been done so far. And this means that if you're higher up on the surface of Mars, there's less atmosphere that you can use to brake. And finally, it's quite hard to replicate Martian conditions on Earth because the atmosphere is very different. So we have also uncertainties in the performance of the vehicle because we can't test quite well on the ground. How do we actually guide the vehicle through the atmosphere? What we need to do essentially when we arrive, assuming that our interplanetary trajectory brought us successfully to the entry interface, we need to transition from hypersonic flight, so at very high velocities, down to supersonic. And we want to do this while steering the vehicle towards a target location, that's our target landing on the surface, while essentially dissipating the kinetic energy that the vehicle has, but respecting heat and mechanical constraints. So if we choose the wrong trajectory, we need to either burn up the vehicle or just to exceed the loads that the structure can support and just disassemble it. And so, for instance, you have these typical curves of velocity, of altitude with respect to velocity, where at the start of entry, you start from very high altitude, and then you have quite a strong deceleration until smaller velocities. Let's see. Okay. The way that this is implemented in onboard guidance algorithms is often by modulating the bank angle of the spacecraft. And the bank angle, so the bank angle is essentially the angle between our lift vector, which is the aerodynamic force orthogonal to the velocity. So it's the aerodynamic force that kind of brings up, and the gravity vector. So essentially, we try to control the lift vector to stay in the atmosphere longer while dissipating the kinetic energy thanks to the atmospheric drag. So we want to do this while gradually decreasing our range to the target, so we gradually get closer. And to keep our direction towards the target, we essentially change the sign of the bank angle. So if you imagine these happening in an actual entry, you will see that the spacecraft kind of does S turns to try and dissipate the energy while getting closer to the target. Ideally, if we didn't have any errors in measurements and in our onboard dynamical model, we will be able to compute the bank angle or any other type of control perfectly, or almost perfectly. And we will be able to do it in one shot because we have control algorithms that are good for this purpose. So essentially, if we had perfect knowledge of the atmosphere and we had perfect knowledge of the current state of the spacecraft in terms of position and velocity, we will be able, for instance, at the entry to compute a control history, which is sigma, that will bring us close to the target. However, since we don't have perfect knowledge on board the spacecraft, eventually we will have that our true trajectory will deviate from our initially computed trajectory. And after a certain time, we will need to recompute the control history so that we get closer to the target. And this is essentially how guidance algorithms work on current spacecraft. However, as to compute the control history, of course, we have to have a dynamical model. So an idea of the dynamics that the spacecraft will encounter during the descent. If the dynamical model doesn't correspond to what we have on board, then we will have, of course, different trajectories for the same control history. Now, if our uncertainty on the atmosphere, so if our essentially our process noise increases past a certain level, what we can do to deal with this is to increase the frequency at which we compute the solutions, so the guidance frequency, to increase the terminal accuracy. However, we can't really do this unlimitedly because onboard computing power is limited, and by increasing the frequency, we're essentially placing harder requirements on the onboard computers, actuators, that makes this approach not robust or economical. Delving a little bit more in depth into the actual sources of the noise. So we said there is uncertainty on the modeling of the aerodynamic interactions of the vehicle with the atmosphere, especially if we want to scale. We have experimental data for current entry systems, but if we want to scale these to very large entry systems, like for instance SpaceX's Starship, that's kind of difficult to do without too much experimental data. Also, we use propulsion systems like retro rockets, and comparing the interaction of these with the flow of the hypersonic flow is quite difficult. But what we'll really focus on here is the atmospheric uncertainty. So let me just play this video. Here, for instance, you can see a map of Mars in terms of surface density along a Martian year. You can see that the density can vary quite a lot. So these areas here, for instance, close to the North Pole, these go up to 3 times the average density during a Martian year. So this means that we have an error. If we took like our density as the average, then we would have an error of 3 times like of the expected force on the spacecraft. So in this work, we will essentially focus on estimating the atmosphere for this purpose. Of course, we're not the first to do this. Offline estimation of the atmospheric properties, such as density, has been done for all recent US missions. And by offline estimation, I mean after the mission is concluded. So after the mission is concluded, you get the data from the landed vehicle on the ground, and then you can process that to obtain the profile of density along the descent. There are also online estimation algorithms in which onboard the spacecraft we have a real-time estimation of the atmosphere in order to improve our control laws. What is noticeable is that so far there hasn't been any approach in which winds have been calculated, which is something particular to our approach. So current state-of-the-art methods for the estimation of the atmosphere at Mars usually rely on the assumption that the profile of the density as a function of altitude is a decreasing exponential. And this comes essentially from hydrostatic equilibrium. And in general, it is a decent model. However, this assumes that the density is only a function of altitude. And in particular, if the density has if we look at the logarithmic plot of the density as a function of altitude, excuse me, in the real atmosphere, we will have something that resembles this red curve here. So by assuming that the density is an exponential, we're approximating this curve with its tangent at different points in time during the descent. So during the descent, we will be decreasing our altitude. So we will be effectively walking along this curve, and then at different times along this curve, we will trace the tangent and assume that the density is along this tangent for all future times. And this is a source of noise, essentially. Yeah, so the actual atmosphere of Mars is more complex. There's a lot of weather and climate phenomena such as dust storms, seasonal variations, and density waves in the high atmosphere. So in general, the density is a function of time, of altitude, of course, the latitude and longitude on Mars. and tau, for instance, which is a parameter that that quantifies the amount of dust that's in the atmosphere due to, for instance, dust storms. If we want to be slightly more formal mathematically, this is actually an inverse estimation problem. So in a controlled entry trajectory, we want to minimize a cost function, which is usually range to the target. For instance, we want essentially to get closer to the target, the distance in terms of the distance on the ground. And our constraints are the dynamics in the most simple case, plus mechanical and heat constraints. And the dynamics generally takes a form that's similar to this, where these are the derivatives of the position vector, and these are the velocity vector. So we have essentially a controlled dynamical system in which our controls are the lift and the drag forces. Now, these controls, since they are provided by the onboard guidance algorithm, these depend on the estimated parameters, which are the estimated density rho and the wind W. You can see that they enter the control forces here. So essentially, the statement of the problem is that we have a set of measurements. For instance, we have inertial measurements that are taken by accelerometers on board the spacecraft for all previous times, previous to the current, because we're imagining of being on board the spacecraft that's currently descending, and we're imagining to try and predict the atmosphere in the future times. So essentially, we want to find the estimated density in winds, minimize the deviations from the actual density in winds that would be encountered. Now, having recognized that this is an inverse problem, we saw that recently supervised deep learning methods have shown excellent performance in solving these kinds of problems, also in other areas such as financial predictions and geological surveying and other applications. So our idea has been to train a supervised deep learning algorithm to estimate arbitrary density wind profiles. Not the classical exponential profile, but something more complex, and do this from onboard measurements. So for the particular type of algorithm, we started by looking at the type of features that we have. I'll go a little bit more in depth on this, in the following slides. But essentially, these are measurements that form a feature vector at each time instant. And so we have essentially a sequence of measurements from 0 to n, where n is the current time. Of course, the particular time in which we have the measurements changes depending on the trajectory. For instance, if we happen to have a denser atmosphere, the flight time will be shorter, and the number of measurements will be smaller. The simplest, in some way, deep learning algorithm is, as you probably know, is a feed-forward network. However, this will require retraining the network once for each value of n, due to the fact that the input layer to the network is a fixed size. Well, the size of these feature sequences varies depending on the sample. Therefore, we decided to adopt the next step, which is a recurrent neural network. And in particular, the recurrent neural networks avoid the issue of retraining by sharing parameters, the parameters of the network across different time steps. So the particular flavor of recurrent neural network that we chose is the long short-term memory architecture. since this prevents gradients from vanishing or exploding during training with reasonable success, at least for the sequence length that we're dealing with here, which is in the order of 100 or 150 time steps. Just a recap, in a long short-term memory network, an LSTM cell, which is a subgroup of feed-forward layers, essentially, replaces the vanilla recurrent layer in the classical recurrent neural network. The task-relevant information, so the information that helps us to decrease the loss during training, is passed along the time steps through the hidden and cell states, which are vectors of fixed length. The LSTM gates, so the layers inside the cell, provide mechanisms for selectively forgetting information or emphasizing other types of information, which helps to prevent the divergence of the gradient. So regarding the data set that we trained the neural network on, we rely on, since data on the Martian atmosphere is hard to come by, we rely on the current state of the art in terms of atmospheric models for Mars, and in particular on the Mars Global Reference Atmospheric Model, or GRAM, as a truth model. And this is a model that is being created by NASA, relies on years of research into the climate of Mars. Using this model essentially allows us to compute the density and the horizontal wind components at any location at Mars. So, for instance, in these maps here, you can see for a section in latitude, you can see these are the maps of density, the east wind and the north wind for a particular time as a function of altitude. We generated 10,000 different instances of the model. So in each instance, we have different density winds as a function of the geographic location, the altitude and time, by randomly sampling the GRAM parameters, which essentially tune the model to deal with different climate conditions. So the next step was to simulate entry trajectories for each of these GRAM instances. We developed a code to integrate the equations of motion, and the controls are provided through the bank angle modulation that I was talking about. And in particular, we use the fully numerical predictor corrector entry guidance algorithm with the target range that's about 500 kilometers from the entry interface. These are actually initial conditions that are modeled on the Mars 2020 entry. We only consider direct entries, which is usually the case at Mars, and a direct entry essentially means that the altitude is a strictly decreasing function of time always. So essentially, we're not with some entry vehicles, such as the space shuttle, for instance, they are able to do skip entries, in which the altitude increases for a part of the entry. And so like the spacecraft kind of skips on the atmosphere so that there's more time to dissipate energy, but we do not consider that in this work. And this turns out to be actually useful, as you'll see in a moment. So for the deep learning algorithm, we define our feature vector to be a vector of inertial measurements. These are essentially the vehicle state, so the position and velocity, the currently measured acceleration by accelerometers on board, and the bank angle that is being commanded to the spacecraft. For the targets, in an ideal world, we would like to reconstruct the whole density wind field for our particular instance, However, this would involve reconstructing functions that are over a 4D domain, which is not particularly computationally efficient, especially if this eventually has to run on board a spacecraft. So what we do is to consider, since the altitude is always monotonically decreasing, we can consider it as an independent variable, and we can consider time, longitude, and latitude as a function of altitude in the density profiles and also wind profiles. So what we do essentially is that we assume that the density of winds are a function of altitude only, but at the same time, the position and the time are varying across these altitudes. And in this way, we manage to catch both time and position-dependent behaviors. And we discretize this altitude interval in 2 kilometers interval in order to keep things contained. You can see here the density and the wind profiles that we get from the sampling of the ground model along with the simulation of the trajectories. Yeah, and essentially we can reconstruct in this way with only 1 degree of freedom. We managed to reconstruct both time and location dependent phenomena. The features are normalized. So each trajectory corresponds to a measurement sequence, and this measurement sequence has to be normalized in order to improve the training efficiency for the network. And these are all the usual reasons that we use normalization for. We don't want to unbalance the loss function towards a specific feature just because the scale of the feature of that feature is different. So with recurrent neural networks, one has to pay a little bit of attention to how the normalization is actually conducted. In fact, the mean of each feature here is computed not only over the samples, this is over the entire data set, but also over time. So we consider, essentially these are summations over each element of the sequence and then over each sequence in the data set. Regarding the targets, with density, we have a small issue, and it's the fact that the density changes usually by a factor of 1 million across the altitude ranges of interest for entry. And also we have to enforce the constraint that the density is always positive. Therefore, we just applied a linear transformation to the density, and we consider our targets to be pseudo-densities. They're a square root of the minus logarithm of the density plus a constant that depends on the units. And this is the resulting target vector, which is a concatenation of pseudo-density and wind components discretized over the set of altitudes that I was showing earlier. And then we perform the usual normalization by subtracting the mean over the samples and the standard deviation. The network architecture is quite simple. There's one recurrent neural network layer, which relies on the LSTM architecture. At each time, we pass the measurements to the LSTM cell. The information from previous time step is passed onwards through the hidden state and the cell state. And at the final time step, we pass the hidden state to a fully connected layer to finally obtain the fixed size target vector. The dimension of the hidden state is 256 units, which turned out to be okay for what we needed. And this is a regression problem, of course. So we chose the mean square error as a loss function, and this is averaged over each mini batch, and also we add a small regularization penalty just to avoid overfitting to the data set. These are the training settings. We use the pre-standard 80-10-10 train validation and test split for 500 epochs, and we had to play a little bit with this in order to prevent overfitting with a constant learning rate and Adam optimizer, and this is a lot of training for train network. However, we can't just stop by looking at the loss and just call it a day, since this doesn't give us a direct indication of accuracy on the density and winds. Essentially, because we are dealing with pseudo densities. That's the main concern. So what we do is to take the network predictions on the test data set after we've trained the network, and we just compute the relative errors with respect to our truth model, which is given to us by Graham. These are histograms of the relative density error and of the relative wind error over the test data set. And these are as a function of altitude, and here you have the density error. You can see here that for higher altitudes, the wind error is larger, something that we'll see in the next slides. To get a general idea of the global behavior of the network over the dataset, we compute the root mean square error, the root mean square relative errors in density and in wind. And we can see that the root mean square errors are pretty good. In particular, the average density root mean square error is below 1%, and for the wind below 5%. And the errors, most of all, are consistent across the training, validation, and testing sets, which means that our network is able to generalize well. We see a little higher errors on the validation and testing sets, but not at a level that really worries us. There are some outliers in the order of 10, that few decades, with the relative errors up to 2% in density and 8% in wind root mean square. If we look at what happens along the altitude, so these are the relative density and wind errors for all samples in the data set. So these are the central line. The continuous line here is the mean over the data set, and here we have 95% confidence bounds as dashed lines. And we can see that the errors are mostly unbiased, except at high altitudes, where we also have a strong variance in the wind error. And this is essentially because of an ambiguity that happens with wind. So at high altitudes, we encounter layers of the atmosphere that are very, very rarefied. So the density is very low. If the density is very low, all trajectories that pass through those layers, since we're starting from the same initial conditions, will experience very small aerodynamic forces, which means that the feature sequences that we're passing to the network will be roughly the same. And this generates a large uncertainty in the predictions of the targets at those altitudes. But overall, this has limited interest for guidance because there's really not a strong effect on the dynamics. So this is all good for the reconstruction of the atmosphere offline. So after the trajectory has concluded. So just to recap, we have, if this is an entry trajectory, we have measurements at various times. We obtain our full sequence of measurements at the final time. We pass this to the LSTM and we obtain density and winds. However, what we would ideally like to do is to go towards an online prediction scheme in which we can pass to the LSTM partial sequences taken along the trajectories and get global estimates of density and winds, at any time for the current and the future altitudes in order to improve the controls that are computed on board. We have started working at this, and if you look at this plot here we have for a single entry trajectory, this is the time, and along time the spacecraft is decreasing its altitude. So for increasing times, we are interested in the future density. So for instance, if we're at this time here, we're interested in this slice of this error surface in density here for all future times. And we can see that although at the final time the error is very low, in the intermediate times the error can be quite large, and in fact comparable with that from an exponential model. This is probably due to the fact that we are optimizing. So our loss function only takes into account samples at the final time, while it really should consider also all samples in between, which might also necessitate an LSTM architecture that's slightly more complex. So this is something that we're currently investigating, and also other things that we're looking into are using gated recurrent units, which I've been told might be more efficient than the LSTM architecture. And also it will be ideal to associate a measure of uncertainty to these predictions. So on board, we will have just the density as an output, but ideally we would like to have a measure of uncertainty so that if the prediction is very uncertain, we can switch to a more reliable method, even if we have lower performance. So in conclusion, we went over a brief overview of entry descent and landing guidance. Essentially, we need to have autonomous control of an entry trajectory on board the spacecraft when it's entering the atmosphere of Mars. And the fact that the atmosphere is uncertain degrades the accuracy and the robustness of the guidance, and therefore we need a method for estimating the density and winds. We chose to use a recurrent neural network for these kinds of predictions, and in particular an LSTM architecture, which has excellent performance which has shown excellent performance in reconstructing density and winds. One thing to note is that I've been told that this is usual, but most of the effort was actually spent on pre-processing the features and targets. So this is in line maybe with practice. And as part of future work, we'll consider the extension of this architecture to online predictions and also associate uncertainty to these predictions. As a final remark, I just saw this morning that actually ESA put out a call for cognitive cloud computing in space. This is not for this particular, it's not related to this particular code in general, but it does seem that even in the space computing field, which is traditionally conservative because essentially of the limited resources that we have for radiation-hardened computers on board, even in this field, we're starting to see increased testing, at least, and flight validation of AI algorithms or machine learning, really. So yeah, this is the end of my talk, and I'll be happy to answer any questions.
Thank you, Davide. And happy to see that, yeah, our field is like expanding in terms of applications also to your field. But let me see if there is any question for now.
Sure.
You can even unmute yourself or type any question in the chat box. Let me see. So I can start. I have a couple of questions, more comments. So my first question would be, when you were showing about the error and the distribution of the error, can you go back to that slide?
Yeah, here.
Instagram, not before. Yeah, this one. So
Okay.
I because at some point I was not sure about when you say the error increases when. So how?
So the error is on these axes here, and so this is just the frequency of each error value over the samples. You can't really see that well because it's all dark here. Sorry for that, but
No, it's okay.
But so what these plots show us is essentially that for when you go to lower values of error, you have a lot of samples with that lower value of error, and while you go towards higher error, you have lower number of samples. And I just thought of plotting this also adding
that one is the number of samples. Okay, because I was like considering the distances in terms of kilometers, and you said that the density was really different on top and then quite homogeneous in the middle. So I was wondering if this is because the network is assuming that what is happening in most of the space is happening also on the top.
There might be. I think that the problem at the top is that we don't really have. So what I'm doing is passing to the network features that are measurements. It's essentially the acceleration that the spacecraft is experiencing. So at those altitudes, the variations might be larger, but if the density changes, since the density is very small, the acceleration of the spacecraft won't change at all. Because if it changes, even if in relative terms it changes by 5 times, it will still be 1,000,000 times smaller than the density that we encounter in the denser parts of the atmosphere. And so essentially in the first parts at high altitudes, the trajectories are all the same. So the features that I'm passing to the network are all the same. So I think it was because of that, but it might be also.
It could be.
There are some. You can see in this plot here, for instance, that there are like some stronger variations in density around the poles for higher altitudes, so that might be.
Okay, interesting. And then before this, you were mentioning at some point that you were also using an algorithm for prediction correction.
Yeah.
Yeah, but I didn't get exactly how do you use that with the LSTM?
No, this is just part of the dataset generation, really.
Okay.
Yeah, no, I didn't go too much into detail on this, but this is just essentially just the statement of the control law in the dynamical system. But it has no impact on, well, it has a small impact actually on the LSTM because this control law gives the bank angle, which is passed as a feature. So if you use a different control law, then you will have a different bank angle history in general. Hopefully, will be similar, but yeah. So the training depends also on this particular predictor corrector algorithm for the trajectory. Yes.
Yeah, actually, we coupled predictor corrector algorithms with LSTM before.
Oh.
And we have seen a good improvement in terms of accuracy. So because it is like what we do for prediction correction is data assimilation. So we used to couple the machine learning with the data assimilation, and we see an improvement because you like adjust the prediction with new information using data assimilation. So
yeah,
so but we can have like a proper chat
yeah,
about that if you're interested.
yeah. No, totally. It sounds like more kind of an. Is it something more kind of an online learning in which you have like a trained network and you have new data and then you want to correct that?
In theory, yes, but we also have been using that in the training part.
Okay.
So
Yeah, would be.
yeah. So we can share like few stuff that we have been doing in other applications.
Yeah. Yeah, totally. It's a very generic algorithm.
Yeah. So thank you. And let me see if in the chat, if in the meantime, there is any question. I don't see any question.
Hey, can I ask a question?
Yeah, of course.
Yeah. Hey, Davide. Thank you for your talk. I was wondering if you consider any other, for example, like an attention network or like a temporal convolution to make these predictions, or what's like future work or what other things you would like to explore?
Yeah, thank you, Cesar. Yeah, so the reason why I went to the LSTM first was mostly because it was performing well and it was already implemented. That's been like a big part, big reason why we also use the LSTM. But I looked into convolutional networks for time invariance because I thought that could be useful for online predictions, but I didn't really have time to implement something like that. But in the future, I think I've heard that gated recurrent units might be more performing for this type of problem that is not, the scale of the problem is not that big. We actually managed to train this LSTM just with CPU and that's it. So that's one avenue. The other thing that I'm really interested in is to associate the uncertainty to the predictions. So ideally, if the network, my idea is that if the network were to see a feature sequence that hasn't really appeared in the data set, it will be able to tell us like, look, the uncertainty on this is very high, so we might be better off using another method of estimation. Since of course the entry process is very delicate, you want to have it very robust.
All right, yeah. So will that be similar to some kind of like fraud detection and like in banking, or yeah?
Yeah, that could definitely be a way of doing it. I think maybe like anomaly detection algorithms. I'm still pretty new to machine learning in general, so I have to learn a lot. Maybe Gaussian processes. But yeah, if you actually have like any suggestion on this, like I would be very happy to hear it.
Yeah, some people, I think, I don't know all of the algorithms, but people use some GANs for fraud detection. And if you want to do something similar, that could be just like Rosella says, a different application.
Yeah, I will look into that. Yeah, thank you.
Yeah, no worries.
And
super,
if it,
yeah,
and
super
then
cool
I will.
work.
Sorry.
Super cool work.
Oh, thank you. Yeah, I would be happy to chat on campus at some point, maybe.
Yeah, for sure.
Yeah, and also in terms of algorithms already implemented, we have as a group our GitHub, and we are happy to share it with other external people. So if you want to take a look and see if there are algorithms, for example, the convolutional neural network that can be useful for you, we can share with you the folder with all the code we have.
That's amazing. Thank you. Yeah, if you can share that, it will be great.
Okay, any other question, comment? So I have to admit that your talk has been really clear. So
Thank you.
Yeah, sometimes people are in a rush and they jump from, from one stuff to another. But I have to say that
Yeah,
so you were like really precise in explaining step by step. Okay,
Thanks.
so if there are no other questions, I think we can thank again Davide for this talk and for being part of our list of invited speakers. And looking forward to meeting you in the campus. And have a good evening to everybody and see you next week.
Thank you, Rosella. Thank you for attending.
Thank
Bye.
you.
Have a
Bye.
good evening.
Bye.
Thank you. Bye.
Thank you. Bye-bye.